Thank you, ma'am. Thank you.
Aravind, this is the time for joining participant. We will start at 2 o'clock. 2
No
o'clock.
issues. No issues.
Yes, good afternoon all. Good afternoon, Aravind sir. Smita teacher, shall we start?
Okay, sir. Okay. Good afternoon,
Nita, shall we
everyone.
start?
Yes. Good afternoon, everyone. Welcome to the last session of our weekly webinar series on instrumental techniques in chemistry, organized by Department of Chemistry, NSS College, Manjeri. I am Smita, Assistant Professor of Chemistry, NSS College, Manjeri. Today, our resource person is Mr. Aravind K, who is working as Assistant Professor of Chemistry, SP College, Changanassery, and will deliver the topic, how molecules behave in UV visible fluorescence and flash photolysis. I am very happy to introduce Aravind K in front of you. And he took his MSc degree in Sacred Heart College, Tevara, and doing his PhD on photoresponsive and theoretical studies on drug delivery systems in MG University. He has 3 years of research experience in dye-sensitized solar cell at Photo Science and Photonics Lab, NIST. And he was a summer research fellow at IIC Bangalore and Jawaharlal Nehru Center for Advanced Scientific Research Institute, Bangalore. And he has 5 international publications and 2 book chapters. Above all, he is a public speaker on science. On behalf of Department of Chemistry, NSS College, Manjeri, I heartily welcome Mr. Aravind K for our weekly webinar series and invite him to deliver the topic.
Thank you,
Please,
Ms.
Aravind.
Yeah, thank you, Ms. for your kind words of introduction, and I'm happy to have been invited by the Department of Chemistry in SS College Manjeri for delivering a talk. So, talking about the importance of chemistry, so I have been asked to take the instrumental aspects of the various techniques, that is UV fluorescence. So, I'll be talking on the point of view of a student, the sense for students especially. I have been told to do so. So we'll go through some of the basics. We'll go through the instrumentation. We'll go through the applications. Thank you, ma'am. And it's actually when you go through the applications or the kind of study which
Aravind.
you do with all these instruments, you'll be able to understand how these instruments are really useful. So my talk is oriented in that particular direction. So talking about the importance of chemistry, you should be knowing the first thing which we do in the morning when we wake up is brushing our teeth, right? So when you brush your teeth, you are actually dealing with polymer chemistry because your toothbrush is basically made of polymer. There's something which I say everywhere. Then you use the paste, which is nothing but gel, which is basically known as gel chemistry. It's kind of a gel, which also comes under chemistry. You use water H2, that is inorganic chemistry, to wash off all what you have used, all what you have used for brushing your teeth. Then the next thing you do is you take a bath. While taking a bath, you use a soap. This is nothing but sodium salt of long chain fatty acid, again organic chemistry. And you wash off all these froth and micelles and soap froths using water H2O, again in organic chemistry. Then you use a textile, which is nothing but a polymer material, which is known as a cloth for taking away all these water. And then for a refreshment effect, what you do is you apply titanium dioxide, nano structure titanium dioxide, which is known as powder, okay, onto your face, so that you will be really refreshed. That is again nanotechnology or inorganic chemistry. Then you have your food, that is food chemistry. It goes into your body, it is biochemistry. And from there you go into your college. I work in SB College Changanassery, but I stay in Ernakulam, which is my hometown. So I travel every day. So while traveling, of course, I use a bus or a train. The metal, the body of which is basically made of metal, again in organic chemistry. Okay, physics people say it is physics which is making all these run, but basically the petrol or the diesel which you pour into it, that is basically organic chemistry. So basically chemistry is the thing which is making it move. Then once you reach the college, what you do is you use a chalk or a board, which is basically a calcium carbonate thing, again in organic chemistry. And nowadays we use plastic boards and pen. The content, the ink of which is organic chemistry, and the whole material is basically plastic, which is again polymer chemistry. So starting from waking up in the morning, that is brushing your teeth, to night, just before you sleep, you drink a glass of water just to prevent heart attack, just to dilute your blood or stuff like that. You are actually dealing with chemistry. So I'm very happy to be a part of the chemistry family by completely understanding its importance. So with this brief introduction, we'll directly go on to a topic, that is how molecules behave. UV visible, fluorescence, and flash photolysis. The reason which I opted for this topic is, one is my experience in this, and the second thing is the fundamental thing which you do after taking your IR, whether your molecule is the intended molecule or not, by just identifying the functional group. The next thing what you do is you take a UV visible absorption. This is a common technique which is used by even in colleges, for degree projects and PG projects. So this is actually a common technique which is used by everyone, and it is that much important. So why not? I thought, why not talk about UV visible spectra? Then connected to that, why not talk about fluorescence? And from there, the flash photolysis, which I used to do while I was working with solar cells. So the topic is actually entitled as how molecules behave. So the reason why I entitled this topic as how molecules behave is actually molecule has a tendency to behave depending upon the kind of radiation it is interacting. So molecule doesn't have any intrinsic property of thinking or something like that, but it has a property of responding to whatever comes in its way. And the major response of this molecule, which we use for studying their properties, is by its interaction with electromagnetic radiation. So as you may know, the electromagnetic radiation, it has a high energy gamma rays at one end, and the low energy or the highest wavelength radio waves at another end. It is actually bifurcated into so many sections. The gamma rays has its own utility, X-rays has its own utility, UV visible and UV as well as visible region has its own utility, which actually comes under the electronic transition, which we are going to deal today. And the near IR region, mid IR region, and the far IR region, or in general, the IR region has its own utility of dealing with vibrational spectroscopy or IR spectra. Probably such a class would have been taken already. Then we have the microwave region, where you deal with the rotational spectra, and ultimately it goes on to the radio wave region, where you utilize all these molecules for communication. So coming on to how this ultraviolet or visible region interacts with the molecule, the answer is very simple. When you shine a molecule with UV light or visible light, the electrons present in the HOMO, that is highest occupied molecular orbital, it gets excited to the LUMO, that is lowest unoccupied molecular orbital. This excited electron has some properties in the excited state, and the de-excitation of which results in so many of the properties, the de-excitation of which can result in so many processes, and all these processes are actually we are actually capable of studying all these processes using various techniques. So we will be highlighting all those techniques which we will be using for studying the de-excitation process which is taking place in the molecule. So when you are dealing with the UV visible or fluorescence or laser flash photolysis, all the fundamentals of this falls under the category of Jablonski diagram. So you probably may be knowing what a Jablonski diagram is. Jablonski diagram actually tells you the various electronic states of a molecule. But when a molecule is said to absorb UV light or visible light, it's not actually the electron alone which is absorbing the radiation. Along with the electron, the molecule as a whole is excited. That's why you name the molecule instead of naming the electron. You name the molecule to be in a singlet state. You say the molecule to be in the triplet state. You say the molecule to be in the quartet state or some other state. And all these naming is given for a molecule. So an excitation for the molecule in the presence of UV region or in the presence of UV or visible light is not only taking place in an electron, but the entire excitation is taking place in the molecule as a whole. That is something which we have to understand. So for the benefit of the students, how the singlet triplet name came, that has to be also told along with this talk. So the name singlet and triplet state actually comes from the total spin multiplicity of the system. In this diagram, in this slide, what you can see is you can see an alphabet S. This alphabet actually tells you the total spin present in a system. The total spin present in the system means if you have a system consisting of 10 electrons, you take the spin of each electron, add it completely. First electron, it should be having plus half spin. Then the second electron is minus half. Third electron is plus half. Fourth electron is minus half. So you take the overall spin, the total spin, by adding the individual spins of all these electrons. You add it, and ultimately the answer will be the total value of S. For a system having 10 electrons, the total number of electrons is 10. So the total value of S will be 0 because plus half minus half plus half minus half, the even number of electrons results in the total spin of 0, as a result of which the spin multiplicity, which is nothing but 2s plus 1, gives a value of 1. Since the spin multiplicity which is defined by the equation 2s plus 1 is giving a value of 1, that particular state is known as singlet state. So if a molecule is actually designated as a singlet state, then you should understand that the molecule is actually completely paired. The electrons present in the molecule are completely paired. There are no free electrons. Then you should understand that the plus half or minus spin. Okay, as I told you, S is the total spin of the system. And if you consider any molecule which is normally in the ground state, almost 99% of the molecules in the ground state are singlet in state, if they are not charged, of course. We are not talking about charged molecule, we are talking about neutral molecules. All these are present in the singlet state because all these molecules are having paired electrons and they do not react. So are there any exceptions? Maybe probably the students can think, are there any exceptions what I said right now, that 99% of the molecules or almost 100% of the molecules are singlet in the ground state? Of course, if you have thought right, of course, the example is oxygen. Oxygen is one particular molecule whose spin multiplicity is triplet in the ground state rather than singlet. When all other molecules in the ground state remains as singlet, oxygen is the only molecule which remains as the triplet in the ground state, which is actually proved by molecular orbital theory. The main advantage of molecular orbital theory when you deal with the spectroscopy is that it is capable of predicting the triplet behavior of oxygen in the ground state. Okay, so I hope you understood the importance of singlet and triplet state. Now we will go through the various possible processes which a molecule will undergo when it gets excited. A molecule always stays in the singlet ground state. All the singlet states are designated as S and all the triplet states are designated as T. So triplet state is a state in which the total spin of the system, total spin multiplicity of the system will be 3. That is 2s plus 1 will be 3. okay, and the value of S will be 1. So if the value of S should be 1, then the electronic arrangement in the molecule should be as which is shown in this diagram. The electronic arrangement of the molecule should be such that there should be 2 electrons which are spinning in the same direction. So plus half and plus half of these two gives a value of 1 to S. So S will be equal to plus half. That gives a value of 1, and 2S plus 1, which is nothing but spin multiplicity, gives a value of 3, and that gives the name triplet for these states. As I told you before, any of the neutral molecule, the ground state should be, will be rather, singlet in the ground state, and ground state is usually designated as 0 with a suffix. So S0 actually represents the ground state of any molecule. S1 represents the first excited singlet state of the molecule. S2 represents the first excited triplet, second excited singlet state of the molecule, and T1 represents the first excited triplet state of the molecule. As you may know, the electronic transitions takes place so fast, okay, that there will be a vertical transition of all these molecules. So in this diagram, each and every electronic state, the S0, the entire thing in the S0 is known as the singlet electronic state of the ground state. This is singlet electronic state at the first excited state, second excited state, and so on. So all these electronic excited states are subdivided into so many categories: 0, 1, 2, 3, 4, and 5. All these are actually vibrational states which are present in the electronic state. Okay, the purest form of spectrum which you can always obtain is rotational spectrum, because it is not intervened by anything. If you are taking vibrational spectra, if you are taking IR spectra, that vibrational spectra definitely will be having lines corresponding to rotational spectrum. And when you come to UV or visible region, which is having a bit higher energy compared to IR as well as microwave, what happens is all the spectra associated with UV definitely will be associated with vibrational transitions as well as rotational transitions. So each vibrational line over here is further split into rotational lines, but in Jablonski diagram we do not highlight that because it's the vibrational lines which gives some important properties over here. So all these electronic states are split up into various vibrational lines, and since the electronic excitations are so fast in the sense in femtosecond range, that is 10⁻⁻15 range, the electronic excitation takes place in a straight manner. And whenever a molecule which is present in the ground state, you always expect the molecule, if it is in the most stable state, if you are not giving any temperature, if it is remaining in the room temperature, not under the influence of any other factors such as pressure, temperature, as I already told you, etc., probably you expect the molecule to be present in the lowest vibrational state, that is 0 state of the S0 electronic state. So when such a molecule is irradiated with UV light or visible light, there a vertical excitation of all these molecules occurs, and from here our spectroscopy begins. So when this vertical excitation occurs, what happens is there are so many phases of this molecule. One phase is the molecule can go up, it can directly come down by de-excitation. Another phase is by the process by which it can come down can be simple vibration. That is one possibility. The molecule can vibrate, and along with the vibration, the molecule can dissipate this energy. Another possibility is the molecule can transfer its energy to some other molecule, which is basically known as quenching. That some other molecule is taking energy from this excited molecule, and the excited molecule becomes de-excited. That is what you use in solar cells. You excite a ruthenium complex, which was my research when I started off in NIST, which I later on dropped because of personal reasons. Anyway, you excite this molecule, and that is actually quenched by TiO2, and the molecule is actually de-excited. So that what do you say? Quenching is another possible pathway. Another possible pathway is the molecule can give the energy as it is in the form of light, which is known as fluorescence and phosphorescence, which we will deal with, which we'll be talking when we deal with fluorescent spectroscopy. So when this molecule is excited, the first thing which you have to understand is no molecule will remain in an excited state which is greater than S1 for a very long time. Maybe even a time which is lesser than femtosecond. The molecule for a fraction of a second in the sense, given time lesser than femtosecond, it goes on to the excited state. Once it reaches the excited state, any other excited state other than S1, that is S2 or S3 or S4, immediately the molecule undergoes an internal conversion and it reaches the S1 state. That is the first thing the molecule does. A molecule never undergoes a sidewise transition. So there is no possibility for a molecule to go to a triplet state directly. but always there is a vertical transition and the molecule gets excited to the highest excited state depending upon the energy which is given. It necessarily doesn't always remain S1, but if it goes to any other excited state other than S1, to S2 or S3, definitely the molecule will come down to S1 singlet excited state, and from there the fate of the molecule is determined. So when a molecule gets transferred from a singlet to a singlet state, the process is known as internal conversion. So by the process of internal conversion, the molecule comes to S1 state, and the problem is the molecule can reach any of the vibrational states of the S1 state. So from starting from S1, S2, just imagine the molecule has reached the third vibrational level. When it gets de-excited, it can directly come to S1 level through internal conversion. It might reach fifth level or fourth level or third level. Even just imagine it has reached the fourth level, as shown in this diagram. Even if it reaches the fourth level, according to Kasha's rule, maybe you can note it down. According to Kasha's rule, once the molecule undergoes internal conversion and reaches the S1 level, definitely the molecule will undergo a vibrational relaxation and reach the lowest possible vibrational level of the singlet state. So the one thing which you have to understand, which you really don't go deep in your academics, is that Kasha's rule. Whichever state the molecule reaches, maybe it's S1, maybe it's T1, the molecule always undergoes a vibration cascading, a vibrational relaxation, making the molecule reach the lowest vibrational level of that particular electronic state. The lowest vibrational level reaching actually results in a decrease in energy of this molecule. So if you give 10 kilojoules of energy to the molecule, definitely there will be a small amount of decrease in 10 kilojoules. From 10 kilojoules, it might be 9.5 or 9.6 just because of the vibrational relaxation, even though the molecule is excited. That vibrational relaxation actually results in a redshift of emission spectrum, which we will be talking about. Once it reaches the lowest possible vibration energy level of the S1 state, the next state of the molecule is, as I told you, either it can undergo again an internal conversion, that is, it reaches back S0 state by simple vibration, which is basically known as vibrational relaxation. That is one possibility. Another possibility is for this molecule to radiate this energy in the form of light, in the form of electromagnetic radiation, and reach the ground state, which is also internal conversion because it is a transition between S and S, S1 and S0. And the radiation, the de-excitation of a molecule by radiating energy is basically known as fluorescence, which approximately takes place in between nanosecond and microsecond, most probably in the nanosecond. The main proof that it is taking place in the nanosecond is, just imagine you have given light to a molecule which is fluorescent. The fluorescence stops immediately when you cut off the light. The same doesn't hold for phosphorescence. Phosphorescence is another process in which, again, the molecule gets de-excited by giving light. But that de-excitation is actually taking place from triplet state instead of single state. So the process is like this. Once the molecule reaches the S1 state or V0 state, if there are energy levels which are having equal energy, something like an equipotential surface which is having equal energy corresponding to V0, and higher excited state energy is corresponding to T1. That is, if the higher vibration energy levels of a triplet state and the lower vibration energy levels of a singlet state coincide with same energy, there is always if the energies are degenerate, that is the accurate word, there is always a possibility for this molecule to go and transfer to the triplet state because they are having similar energy. When the similar energy is resulted, what happens is there is always a possibility for this molecule to go from the singlet state to the triplet state. Once it reaches the triplet state, what happens is again a vibrational cascading is resulted. It reaches the lowest possible vibration level of the triplet state, which is again Kasha's rule, and from there it can emit radiation. And if it emits radiations, it is basically known as fluorescence, phosphorescence, which actually takes place in millisecond to microsecond region. And this phosphorescence always exists even after the incoming light is cut off. It actually exists for a longer time compared to fluorescence, because fluorescence takes place in nanosecond and phosphorescence takes place in micro to millisecond. So this is basically the fate of all these molecules. So if you have to learn the fate of molecules in the excited state, how the molecule goes to the excited state, basically that is dealt with UV visible spectra. And if you are trying to learn how the molecule emits light, if the molecule has a property of emitting light, how the molecule emits light is actually dealt with fluorescence spectroscopy using fluorimeter. And if you are so much keen in understanding how the molecule behaves in the excited state, by keeping it in the excited state, you use laser flash photolysis. Laser flash photolysis is seldom used compared to UV visible as well as fluorimeter technique. You know what is an electronic absorption? We'll just brush up through all these. Electronic absorption is nothing but the total energy of the molecule according to Bohr-Monochromator approximation is divided among E electronic, E vibrational, E rotational is something which is known to you. And when the molecule is actually excited, what happens is all these electronic states are excited, and the frequency corresponding to excitation, the wave number corresponding to excitation, is given by this formula. There is something which you study in your BSc as well as MSc level. And from there you go on to Frank-Condon principle. You know what a Frank-Condon principle is. When you analyze all these absorption spectra, what you can always see is certain vibrational levels are having a higher intensity compared to the expected vibrational energy level. This is the Morse potential diagram, Morse curve diagram for the ground state as well as the excited state. You normally expect the molecule to be excited from the lowest possible state of S0 state to the lowest possible state of the first excited state. So normally what we expect is the 0 to 0 transition should be having a higher energy or a higher intensity, and not higher energy, I'm sorry, higher intensity. So that transition should always be having a higher intensity is our expectation, but our expectation is totally different from what science teaches us. Hence, we deal with Frank-Condon principle. So Frank-Condon principle is another reason why a molecule doesn't go to triplet state directly, which we will be dealing in laser flash photolysis. So triplet state directly, always a singlet vertical excitation takes place, because according to Frank-Condon principle, a molecule undergoes UV visible absorption so fast that there will be very less time for the nuclei to move. That means the bond distance doesn't change during an electronic absorption. So in the ground state, if you go on with the quantum mechanical calculation, the probability of the molecule is to stay at the middle, at the center, where there is maximum probability according to psi squared in the V0 state. So when the molecule is excited, the molecule will be reaching that vibrational state where it can directly go vertically. Four possibilities for Frank-Condon principle is this, in which the internuclear distance in the excited state is same that of the internuclear distance in the ground state. Second diagram, internuclear distance in the excited state is lesser than the internuclear diagram in the ground state. And the third and fourth diagram, the internuclear distance in the excited state is higher, and in the fourth diagram, the fourth picture, it is the highest. Okay, and out of these two possibilities, the second possibility is always abandoned, because it is very hardly rare. It is very, 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 very rare for a molecule to have an internuclear distance lesser than those in the ground state when it is excited, when it is having high energy. So this diagram is not taken into consideration. This possibility is also very rare, because whenever you excite the molecule, of course, the internuclear distance definitely changes. It undergoes a faster vibration. So these two diagrams are equally valid, and these two diagrams are equally valid for Frank-Condon principle. From there, you have something which is known as dissociation. If the excitation of all these molecules takes place to that vibration level which correspond to the dissociation of the molecule, then you call it a dissociation level. And another concept which you deal with the Frank-Condon principle is the pre-dissociation. That is, you excite a molecule from the ground state, you go on to the first excited state, the first or the second, just imagine you are going to the first excited state to a particular vibrational state. That particular vibrational state is stable in the first excited state, but just imagine you have another continuous state which coincides with the energy of the first, that particular vibrational state where the molecule has come. Since this another excited state which is having a dissociation limit corresponding to the energy of the vibration where the molecule is sitting now, even though you don't intend the molecule to dissociate, the molecule, since it is a degenerate energy level, it transfers itself into the another unexpected energy level, and it undergoes dissociation. And this condition is basically known as pre-dissociation. Okay, and from there we come on to the crux of the UV visible absorption spectra. The UV visible absorption spectra always is based on Beer-Lambert's law, And Beer-Lambert's law is something which is known as I is equal to I0 into 10 raised to minus epsilon dc, where epsilon is the molar extinction coefficient, d is the thickness, that is the path length of by which your light moves, and c is the concentration which you use in colorimetry also, right? The same principle holds for the UV visible absorption spectrophotometer also. So whenever you get a chance to go on to any of the labs, it is always better to visit labs, because touching an instrument, experiencing it by seeing it, is totally different from learning the theory of the instrumentation. So this is how a UV visible chamber looks like. If you have a UV visible spectra in your college, of course, just go through it, and in the presence of teacher, please do it. And here you can keep the samples, and this is the monitor where you use you take the UV visible absorption spectrum. As I told you, absorbance is measured according to epsilon CL, where C is the concentration, L is the path length, and epsilon is the molar absorption coefficient. Now coming on to the instrumentation of UV visible spectra. Basically, the various parts of UV visible spectra are highlighted over here. It actually has a radiation source. Okay. Now what we have to see is the what we actually want is we have to find out where the molecule absorbs. Why is that important? Various functional groups absorbs in various regions. Okay. So this can be used as a preliminary identification, not a confirmatory, though preliminary identification technique for identifying the functional group. That is one important thing. If you have any kinds of transition, pi transition, n to sigma star transition, sigma to sigma star transition, MLCT transition, LMCT transition, if you want to know how a solvent changes the behavior of the molecule, how a solvent changes the excited state of a molecule, how the introduction of a functional group differences make a difference in the electronic spectra of the molecule, by introducing an NH2 group, if you want to know, by introducing an NO2 group, if you actually want to know how the various excited state changes its energy level, you can use UV visible spectra. You can use the data which you obtain from UV visible spectra. We'll go to applications also. So the first thing is you have to supply energy to the molecule. Since it is utilizing UV as well as visible region, you have to take up lamps which is capable of supplying UV light as well as visible light. Deuterium lamp, hydrogen lamp, tungsten halogen lamp, xenon lamp, tungsten filament, and mercury vapor. All these are various lamps. It depends upon the company and the instrument which you use. All these varieties of lamp or a combination of these lamps are actually used for producing UV as well as visible light in your system. And again, after the radiation source, you require something which is known as an optical system. The optical system definitely consists of a monochromator. It consists of a fluorichromator. It consists of inlet lens. It consists of inlet slits, exit slits. You have collimated lens. You have diffraction grating, etc., which we will be dealing when we go on to the diagram, instrumentation diagram. Then you have the detector. Once the light which comes from the sample, it passes through the optical system, it then passes through the sample, and after the entire light passes through the sample, the light which is coming out of the sample is actually being detected by the detector, and this detector is basically a photomultiplier tube or a photodiode or whatever it is, which again depends upon the instrument. So these are the various detectors which are used, and the most important detector is photomultiplier tube, which is used as a detector. And the method which you use for keeping a sample is a small cuvette, which is made up of quartz or silica or glass or polythene or whatever it is. That again depends upon the instrument which you are using. For a standard instrument, deuterium lamp is used basically for giving out UV light. Tungsten lamp is used for giving out visible light. So the basic instrumental layout is like this. When you switch on the instrument, you have deuterium lamp as well as tungsten lamp activated. This deuterium lamp as well as tungsten lamp, it gives light to the filter. This filter, what it does is, the instrument is operated in such a way, normally a normal UV visible instrument is operated in such a way that one wavelength is led through the instrument for reaching the sample at one particular time. That is, once you switch on the instrument, you go to the software which deals with the instrument, you give the range of wavelength. So when you keep the sample, you switch on the instrument, you switch on the process, what happens is, if you have given the range of 300 to 600 nanometer, first 300 light is passed through this, then 301 nanometer light is passed, then 302, 303, 304. So in each step, that particular wavelength of light is transferred. But the problem is that deuterium lamp and the tungsten lamp doesn't know which wavelength it is transferring, because it is giving UV light completely the tungsten lamp is giving UV light, the visible light completely. So it is the filter. The filter which actually filters the light which we actually require. But the filter is actually nothing but a WebGear. It actually is capable of filtering only in that particular region. So what the filter does is it filters the entire light which is coming from the deuterium lamp or the tungsten lamp, and what happens is that particular range of wavelength is given onto the monochromator. So what the monochromator does is the monochromator from that particular range which the filter has given, from that particular range the monochromator cuts down all the wavelengths and it passes only one particular wavelength, the desired wavelength, to pass through it. And once that desired wavelength, for example 300 nanometer, so UV light is being produced, the filter cuts off all the other light, passes the UV spectrum, and the monochromator passes that particular wavelength, probably 300 nanometer, to pass through the monochromator slit. So the 300 nanometer slowly moves on to the beam splitter. In the beam splitter, what it does is the entire light is split into two. That monochromated collimated light is split into two. It actually, the splitter splits the light into two, and one part of the light passes through the sample and another part of the light passes through the reference. Here sample and reference becomes very important, because when you are dealing with a UV visible spectra, solvent has a very important effect. So in whichever state you are taking, the molecule, maybe the solid state, you can actually take a reflection spectra. In the liquid state, the gaseous state, of course, you don't take. So solid state and the liquid state, usually you will be using the UV visible spectra for the liquid state. So in the liquid state, when you are taking, you usually dissolve your molecule in a solvent. And the problem is the solvent also has a tendency to absorb in all these ranges, UV range. So what we have done is we always keep a reference of the same solvent which is used for to prepare the sample. So sample is dissolved in a solvent, that solvent is kept as a reference. So the incoming light which is split by the monochromator is actually passed through the reference as well as sample, and the light which is coming out of the reference as well as sample reaches the photodiode or the photomultiplier tube. And by analyzing these two lights, by taking the difference of these two transmitted light, you will be able to understand what light the sample has been absorbed. So basically, the deuterium as well as the tungsten lamp, it gives UV as well as visible light. So this UV as well as visible light is actually initially filtered using a filter, and from that filter, the desired wavelength, that is the 300 nanometer or whatever wavelength which you require, or the range of wavelength which is given, each wavelength is given to the beam splitter individually by using a monochromator or a diffraction, which we will be looking into. And from there, you have a beam splitter. This beam splitter splits the light into two. One passes through the reference, another passes through the sample. The reference is important because the solvent also produces an absorption. Our aim is to find out the absorption of our sample alone, our molecule alone. By taking the difference in the absorption, you will be getting the absorption spectra of the molecule. That sums up the instrumentation of the UV visible spectra. Here you use something which is known as monochromator. The monochromator you have, this is the basic structure of a monochromator. You have an entrance slit. The light which comes from the filter, it enters through the monochromator. It passes through the diffraction grating, which is shown over here. And once the diffraction grating results in producing one particular light, it goes out through the exit slit. So this is the entire diagram of a monochromator, and this is the diffraction grating. Normally, diffraction, we always deal with diffraction. We take the example of a solar eclipse or a lunar eclipse, right? So the light from during solar eclipse, the light from the sun, it gets diffracted, it's from the moon, and that diffracted light will be reaching that. That is the normal example which we give. But there, the light is actually diffracted from the edges of the moon, okay, and it is reaching the earth in a focusing fashion. But normally in UV visible spectra, the diffraction is actually in a reflection form, and the reflection diffracting has so many triangular shaped slabs which is kept like this. So when you switch on the instrument, what happens is the spacing between the triangular space slab, the spacing is actually being adjusted, and the difference in the spacing, which is D, it results in the various wavelengths. So the diffraction grating is set into that particular instrument such that it is capable of producing the desired wavelength when the instrument reaches or demands that particular wavelength. So the difference in the D actually results in the various wavelengths which is produced by the diffraction grating. By changing the value of D, what happens is the combination of the reflected wavelength is differentiated, And one particular wavelength is actually produced using the diffraction grating. So the diffraction grating is actually the so-called murmur of the so-called UV visible spectra, because it actually gives you the desired that particular wavelength only. And once that diffraction grating by changing D, which is controlled by the instrument, that particular wavelength is observed, it goes pass through the sample, and once it passes through the sample absorbs light, and the transmitted light, which is different from that which is absorbed. The transmitted light in the sense the light which is not absorbed by the transmitter, it reaches the photodiode. Photodiode and photomultiplier tubes, they both are used as detectors. The photodiode, it produces one electron from one photon, but a photomultiplier tube, it multiplies the electrons which the photons gives. Actually, photomultiplier tube is the most reliable detector which you use in UV visible as well as flat photolysis as well as fluorimeter. The most reliable in the sense, the intensity of the light which is coming through the sample and the intensity of the light which is coming to the reference will be very less. So since the intensity is very less, for a plausible amount of detection, for a plausible amount of calibration and data retrieval, you have to multiply, you have to amplify the so-called light. So the basic amplification is taking place in photomultiplier tube, which is absent in photodiode, because photodiode, when one photon comes and falls, one electron is generated. But in a photomultiplier tube, the working principle is different. When an incoming photon comes and falls onto an electrode, which is basically an electron is actually being generated, that electron hits onto a dynode, which generates more electron, which goes on hits onto another dynode, and you have a series of dynodes like this. And ultimately, when it reaches the anode, you have a stream of electrons, and the energy or the intensity of the electron is directly correlated to that photon which is falling. So the entire intensity of the electrons and its energies is actually related to the light which is falling onto this photomultiplier tube, which is the detector. So by looking at the intensity of the electron and its energy, you have a direct correlation between the light which actually fell onto the detector. Since you have so many electrons, since you have an intensity being multiplied, what happens is the detection becomes very easy and the analysis of the result is very nice. So coming on to the application of UV visible spectroscopy, as I told you, if you have any impurities in your molecule, one method is by using UV visible spectra. Just imagine you go and purchase something which from your market, you are reluctant to use it because you think that you have some impurity. Okay, you take the pure sample, you take a UV spectra, you take the sample which you got from the market, you take the UV spectra. If there is some difference, definitely there is some impurity. So detection of impurities is one such application. Structural elucidation of organic compounds. Structural elucidation in the sense it is not accurate as like NMR or something like that. If you have any functional group, if you have a possibility of an MLCT or LLMCT transition, all such transitions can be identified using UV visible spectra. And quantitative determination of compounds. Quantitative determination of compounds means there is another application. Quantitative determination means something which you do in your lab. Colorimetry, estimation of chromium. I suppose it is used. It is done by using colorimetry. That is, a nickel complex or something like that. You first prepare a graph of known concentrations. You will be getting a straight line graph, and when your teacher or your examiner actually gives you an unknown concentration, by extrapolating from the graph, you will be getting the unknown concentration which is given to you. So that graph is actually plotted using a concentration as well as the absorbance which you obtain from your UV visible spectra. So the UV visible spectra, since it depends upon the epsilon CL value, concentration value, this can directly be used for quantitative determination of compounds as well. Another important aspect of UV visible spectra is the solvent effects can be easily be studied, because many organic reactions are solvent sensitive. Okay, we are actually dealing in a world in which we always like to use water, but water cannot be used always. Solvent sensitive reactions are there. If you use the solvent, if you change the solvent, the yield is really matters. So what happens to a molecule's excited state? Homo, LUMO, homo plus one, LUMO minus one, I mean LUMO plus one, homo minus one excited state. What happens to that? All such factors can be dealt with UV visible spectra, because the absorption spectra of a molecule in water will not be same as the absorption spectra of the same molecule in ethanol, because this ethanol has some kind of interactions with the HOMO as well as LUMO. Compared to that of water, the interactions will be different, as a result of which The absorption spectra will be different. The absorption wavelength will be different. Okay, so such things can be studied. So this is an interesting spectra, which is from my published paper, which long back, very long back from NIST. I'm a co-author of this paper. Let's imagine that we have plotted an absorption spectra of this molecule. This molecule is actually peculiar. It has a bipyridine. It has a double bond over here, an olefinic bond, and it has an NCS3 twice group. NCS3 twice group, the nitrogen atom, it has a lone pair. It is actually a donor system, and this actually acts as an acceptor system. Since you have a donor acceptor system, there is always a possibility of a charge transfer transition which is taking place from this nitrogen to this nitrogen, right? So this actually represents the UV visible spectra. UV visible spectra is always plotted by absorbance in the y-axis to wavelength in the x-axis. This actually explains the UV visible spectra of the molecule at various pH conditions. You can see that when the pH is very high, the peak at approximately 380 nanometer is very high, while the peak of the same at 500 nanometers, approximately 490 nanometers low. But when you decrease the pH, when you make the solution more acidic, when it reaches 3.6, the peak value at 380 nanometer, it goes drastically down, and the peak at 480 nanometer goes drastically up. Hope you can find the difference. And you have an isosbestic point over here. You leave that, so by comparing these two peaks, you are actually studying the pH dependent absorption, pH dependent behavior of all these molecules. Can you presume what has happened over here? Just think for maybe 5 to 10 seconds. Okay. The answer is this. When H plus is given to the molecule, which is more basic? Are these two nitrogen more basic or this nitrogen more basic? The NH2, the primary amine, it has its lone pair which is circulated in the, your aromatic ring. Hence, these two nitrogens are actually highly basic, as a result of which the H plus goes and coordinates down to this molecule. Once this coordination happens, what happens is the electron density over here slowly starts shifting to the H plus over region, because you have a positive region right here now, and there will be a very high charge transfer transition which is taking place from the primary amine nitrogen to this region. That charge transfer transition increases when you decrease the pH. The solution is more acidic, the more positive charge is over here, more molecule will be in this particular fashion, as a result of which a high intensity charge transfer transition can be expected. But when there is no charge transfer transition at all because of H plus, when there is minimum charge transfer transition, this will be the absorption spectrum of the molecule. That is your absorption, which is due to the nitrogen. This particular group is being portrayed at 380 nanometers. So UV visible spectra can be used to study the pH dependent behavior, temperature dependent behavior. So many kind of behavior can be studied. It all depends upon how you want to deal with the system. So you have a wide variety of application for UV visible spectra. Then you come on to fluorescent spectra. Fluorescent spectra usually deals with fluorescence, phosphorescence, bioluminescence, chemiluminescence, etc. Okay. So as I mentioned earlier in your Jablonski diagram, the vibrational equilibrium before fluorescence results in some loss of excitation energy. As I told you, your molecule, if you can close your eyes and think for a moment, the molecule gets excited to the excited state, to any S2 or S3 excited state. It undergoes an intersystem closing. It comes to S1 excited state. Probably I'll go back to that particular slide. S1 state. And once it reaches the S1 state, definitely it has to undergo a vibrational transition. So the internal conversion itself results in loss of energy. And from there will be definitely another loss of energy due to the vibrational cascading before the molecule reaches, after the molecule reaches the V0 state of S1 state. As a result of which, the fluorescence or the emission spectra always results in a higher wavelength, or a Stokes shift is always expected for the emission spectra for the fluorescence. So emission spectra is nothing but it is similar to what you observe in the absorption spectra. The only difference in the emission spectra and the absorption spectra is the absorbance is changed by emission. So here you are seeing what the molecule absorbs, and in emission spectra you see what the molecule emits. That is the only difference between UV spectra and the emission spectra. And there is always a Stokes shift because some amount of energy is naturally lost, And the emission, normally what we expect is if you give a molecule 10 kilojoules of energy, when the molecule comes down, it should be giving us back that the very same 10 kilojoules of energy, which is not being expected in fluorescent spectra because of the so-called reasons. And always a Stokes shift is actually expected. And this is the fluorescence time-dependent delay of fluorescent spectra, and the fluorescence decay time. We are running short of time, I know, so I am skipping off all these topics. And the fluorescence intensity is given by a formula which is similar to that of your what do you say, Beer-Lambert's law, which is given by phi into I0 into ABC, where ABC are molar extinction coefficient, the volume as well as the concentration, and you have the formula directly. We directly go on to the instrumentation of fluorescence spectra. Here, the instrumentation of fluorescence spectra is thought-provoking because the instrumentation over here is very similar to that of absorption spectra. Okay, an addition to an absorption UV visible absorption spectrophotometer in fluorescence spectra is you additionally have a monochromator after the sample emits. In the absorption spectra, you have a light source, tungsten light source or deuterium light source or whatever it is, which is capable of giving UV light as well as visible light. It goes on through a filter, goes through the monochromator, okay, and from there it goes on to your sample. Okay, once it goes on to your sample, you have a sample as well as a reference over there, because you have to subtract the effect of reference over there. Here you don't have any reference at all. See, here you directly give the sample as such. Okay, and you have a sample over here, and once the sample emits, you know what happens is the sample, the emitted light of the sample is observed one wavelength at a time. That is which is being utilized in fluorescence spectrophotometer or fluorimeter as a whole. So initially in the UV visible spectra, you are giving one particular wavelength, one at a time, 300, 301, 302, 303 to the molecule. In fluorescence spectra, what you are actually doing is you are measuring what the emission of the molecule will be at 300 nanometer, then at 101 nanometer, then at 302 nanometer. So this monochromator, which is the monochromator which is kept after the sample is excited, is being utilized for that. So when the excited sample de-excites and emits fluorescence or phosphorescence, whatever it is, the emitted light will be having a range of frequencies. So the detector, which is again a photomultiplier tube, actually detects one wavelength at a particular time. Just imagine your molecule emits at after 500 nanometer. Maybe you are observing the emission from 500 to 800 nanometer. So you are exciting the molecule. Once you are exciting the molecule, you are asking the molecule to emit the radiation, the molecule emits. Then you start observing the intensity at 500 nanometer. You plot it. Then you observe the intensity at 501 nanometer. You plot it. Then you observe the intensity of 502 nanometer. Then you plot it. Then you observe the intensity of 503, and it goes on up to 800 nanometer. So here, compared to UV visible, there is no need of giving one particular wavelength one at a time to the excited molecule. Okay, the first thing which you have to keep in your mind is always a UV visible absorption spectra should be taken before you use a fluorimeter, just because fluorescence actually is given by the molecule once the molecule is excited. So if you want to know where the molecule is to be excited, if you want to know the correct wavelength where the molecule is to be excited, you have to take an UV visible absorption spectra. Once you take the UV visible absorption spectra, is there any necessity of giving every wavelength? No, right? You are required to give only that particular wavelength where the molecule has maximum absorption. For example, if you take this particular example, just consider this absorption spectrum, only this absorption spectrum. You know that the molecule absorbs at 380 nanometer. So when you are using a fluorescence spectra, instead of giving all the value from 300 nanometer to 800 nanometer, it is more than enough and more than sufficient just by giving 380 nanometer from this light source. So light source gives everything. Your monochromator is adjusted in your instrument such that a 380 nanometer flashlight is actually given to the sample. Only 380 nanometer is given. Why 380 nanometer is given? The molecule has maximum absorption at 380 nanometer, which the UV visible spectra told us. So 380 nanometer is specifically given. So the monochromator does not have that much particular work. The diffraction grating over there is adjusted just one time for that particular molecule. The sample gets excited, and once the sample gets excited, just see the direction in which the monochromator is kept. See, earlier when we were dealing with the UV visible spectra, the photomultiplier tube was in straight line with the monochromator, right? The initial monochromator, the photomultiplier tube was in straight line. Just see the arrow or the cursor which I'm pointing to. This would be a region where the photomultiplier tube was kept, the analyzer was kept. But in fluorescence, the analyzer or the monochromator is actually kept perpendicular to the sample. This is because when 380 nanometer light passes through this, some light definitely may not be absorbed by the sample. Of course, there will be Raman scattering. There will be so many scattering, taking place in this molecule. All the scattering takes place, and it actually is taking place in all the other directions. And the incoming light direction is actually completely cut off. And to cut off the incoming light direction, this emission is always taken perpendicular to the incoming light. Otherwise, the detector will always detect incoming light also. So instead of detecting the incoming light and cutting it off, it is always better that you observe the emission at right angles to the incoming light. That is something which is used in UV visible spectra. So this is something which you have to keep in your mind. Okay, and these are the QH which are used for UV visible spectra. For fluorescent spectra. For UV visible spectra, two-sided QH are fine. Two-sided QH in the sense this is actually a four-sided QH. Four-sided QH means in all the four sides the QH is transparent. There are QHs which are lesser in amount, in which only two sides are transparent. That is more than enough for a UV visible spectra, because light enters from one side, it goes out through another side. That is all what UV visible spectra is doing. But for a fluorescent spectra, you definitely require a four-sided QH, because when the light enters through one direction and it goes out through the other direction, the fluorescence is actually measured in the perpendicular direction, and hence all the four sides of the QH need to be transparent. So if you are trying to install any fluorimeter or in your college or in your institution or something like that, always keep in mind that two-sided QHs are useful only for absorption, while four-sided QHs are a necessity for fluorescent compounds also. Here also the light source can be mercury arc lamp, xenon arc lamp, tungsten lamp, and you can be a tunable dye laser also. Laser normally aren't used because mercury arc lamp, xenon arc lamp, and tungsten lamp, they are actually lesser costly compared to that of laser. And monochromators and filters and the QH, as I told you, it is all very similar to that of UV visible absorption, and the detectors which are used are photomultiplier tube. And this is an example of absorption and emission. The same molecule, the absorption as well as emission is plotted in this particular diagram. So the same molecule absorbs in this region. It has a common region over here, spectral overlap over here, and the emission of the molecule. You never expect a fluorescence emission to coincide with absorption, and always you have a Stokes shift, because there is a de-excitation of the molecule taking place in the higher levels, higher excited electronic levels, as well as vibration levels to a lower energy levels, which actually results in the Stokes shift, which is observed in fluorescence. So what are the application of all these molecules? So fluorescence, applications of fluorescence are also useful. Any molecule, one of the major applications which I presently use in my thesis, I am almost submitting my thesis. One of my polymers, which is communicated to macromolecules right now. It is like the polymer actually has an emission at approximately 470 nanometer. When the molecule aggregates in one particular solvent, the aggregate actually results in increase in emission. Okay, so this is a molecule, an example of a molecule. I took it from some paper, I don't remember. This is the molecule which the authors have reported. When your molecule is aggregating, the aggregation results in emission of this molecule. So just by looking at the emission spectrum, you can actually analyze whether the molecule is aggregated or not. So the aggregation of the molecule, the drug release study of the molecule. Just imagine you are using a fluorescent molecule, a molecule which is capable of emitting light, fluorescence or phosphorus, something like a curcumine. So if you are taking curcumine as a drug, a curcumine, you load it into your polymeric system or a delivery system, and a free curcumine gives an emission, and the curcumine which is loaded into your drug delivery system inside your delivery system gives some other emission. You are giving some sensitivity such as pH or temperature or whatever it is. You are asking the delivery system to release the drug. by just monitoring the emission spectra of your molecule, you will be able to say, you will be able to predict whether the drug has come out or not. There are so many applications of all these fluorescent spectra which you can go through. And the next part, when I was dealing with solar cells, I was more interested in how these molecules behave in the excited state. Now, the UV visible spectra actually deals with the behavior of the molecule in the ground state, how the molecule absorbs when the molecule is present in the ground state. Okay, and fluorescent spectra actually tells you how the molecule behaves once it reaches the excited state and it comes down. So we have dealt with the behavior of the molecule while going up, and we have dealt with the behavior of the molecule while coming down. Now we are going to deal the behavior of the molecule which behaves when it is staying at the excited state. So going is dealt with from ground state to excited state, is dealt with UV visible spectra. Coming down is dealt with fluorescent spectra. At the excited state is actually used by laser flash photolysis. Just imagine you have to study a free radical or excited triplet state, which exists only for millisecond or microsecond. Just imagine you have to find out the excited singlet state of the molecule, which exists for nanosecond. Just imagine you have to do some electron transfer processes. There are so many processes, including photosynthesis, in which the electron transfer processes take place in picosecond or femtosecond. How are you going to study? So if you want to study such ultra fast processes, you should be using an instrument which is more sensitive, which is more fast than the process which is being taken. Correct? So by using a UV visible spectra or a fluorescent spectra, it is not enough, because all that takes place in millisecond or microsecond, maximum nanosecond. It does not deal with any excited state of the molecule. So now you are using an instrument. We are going to deal with an instrument which is known as laser flash photolysis, which is faster than any of the processes which I mentioned over here. There are so many laser flash photolysis system. We have a nanosecond laser flash photolysis system, in which the laser flash system is used to study energy states present in the nanosecond. We have picosecond laser flash photolysis system. We have femtosecond laser flash photolysis system in IIT Chennai. I have been there for studying some of my molecules in femtosecond laser flash photolysis system, because many of my ruthenium complexes were not having any kind of a triplet property or something like that. As a result of which, all these excited state were singlet. So I was forced to do femtosecond laser, and the technology is completely different. So this is a general diagram of a laser flash photolysis. The diagram of the laser flash, this is the laser, and you have a motor sound when you switch on the laser, and excuse me, you actually require more than 1 hour to switch on the laser if the laser is not turned on. 1 to 1.5 hours is actually required for the instrument to operate. So this is actually a general picture of laser. The laser which is usually used in all these systems, femtosecond, nanosecond, or picosecond, the instrumentation of which is very complicated, because from femtosecond to when you go from nanosecond to femtosecond, I mean picosecond, and from picosecond to femtosecond, you have some additional filters and additional slits which are used to cut short the time. In all these lasers, you use Nd:YAG laser, neodymium yttrium aluminum Nd:YAG laser. Nd:YAG laser actually gives you a high intensity pulse of 1064 nanometer, and in the laser, all our molecules, as you know, it doesn't absorb in 1064 nanometer. If you are capable of making a molecule which is absorbing at 1064 nanometer, probably you will be a king, because it can directly be used for making solar cells, because NIR region dyes are having very high demand. It can be used for photodynamic therapy also. All our molecules definitely will be absorbing in UV region and still a visible region, as a result of which the high intensity pulse in the laser can be frequency doubled to 532 nanometer and 355 nanometers. So we have a laser source which is capable of producing light either at 1064 nanometer or 532 nanometer or 355 nanometer, and depending upon the molecule which we are using, almost all the molecules will be having an absorption at 355 nanometer, which we are dealing with, and many of the molecules will be having an absorption at 532 nanometer. Just for the sake of saying something, a particular value, we will go on with 355 nanometer. So what you do is you adjust your laser flash beam to 355 nanometer, and you keep the sample. When you keep the sample like this, a laser actually produces a flash of 355 nanometer. Just a flash. When you switch on the instrument, a flash of 355 nanometer laser is produced in the sample. So a very high intensity of 355 nanometer, when it falls onto the sample, just imagine what happens. Since the intensity is very high, almost 80 to 90% of the molecules which is present in the sample, it gets excited to the first excited state. Okay. Immediately after the laser is flashed, the molecule is excited, and immediately the xenon arc lamp, which all those filters and something which we used with which we used with UV visible spectra, are used to analyze the molecule which is present in the excited state. So instead of using so if you take away the setup of this, your laser setup or this prism, etc., the entire remaining thing, which I am highlighting using my cursor, is basically a UV visible spectrophotometer setup. Okay. The only thing is that in the UV visible spectrophotometer setup, here you are using a ground state sample, but in laser flash photolysis, you are actually using a laser to make the sample excited. You are keeping the sample in the ground state. You are using the laser to excite the sample in the excited state, and by some combination of all these instruments, what you are doing is you are keeping the molecule in the excited state. At the instant the molecule is excited, you are taking the absorption spectrum. And the absorption spectrum over here, there is a small small problem by taking absorption spectrum over here. The problem is, as that of the UV visible spectra, you cannot give one wavelength at a time, 300 nanometer, 301 nanometer, 302 nanometer, because giving at one particular wavelength at a time is a tedious process. So what you do is the entire wavelength from the UV as well as visible region is given to this molecule in a fraction of a second, within no time. And that is actually synchronized with the laser flash. That is what the instrument is doing. Immediately after the laser is flashed, the xenon arc lamp, it gives the light again in a flash. And when that light is given in a flash, these two are synchronized such that the molecule at the excited state absorbs the light which is given from the xenon lamp simultaneously. The excitation as well as the absorption takes place simultaneously with the synchronization, and ultimately you will be getting an absorption spectra of the molecule in the excited state. That is what laser flash photolysis is doing. So this is my paper, this is my molecule which is not reported yet. The quantum yield of this molecule was very less. So this is something which is known as a transient decay spectra. That is, once the molecule is excited at one particular wavelength, what happens is the molecule decays slowly, and this decay is actually observed as in the form of a graph. By taking the average of this particular thing, you will be able to observe that the molecule has a very less decay time of maybe 0.1 microsecond. The molecule has a very less decay time of 0.1 microsecond, because we take the average of the middle portion of this and we note the time, and that will actually gives you the excited state lifetime of that particular molecule. So this transient absorption spectrum actually represents the absorption spectrum of the molecule when it is present in the excited state. The normal absorption spectra represents the molecule when the molecule is present in the ground state, and the transient absorption spectra represents the presence of the molecule in the excited state. So so these are the two important data which you obtain from laser flash photolysis studies. I'm rushing through that. Another important aspect of laser flash photolysis study is that you will be able to monitor what do you say, the electron transfer processes. My dye is actually a ruthenium dye, the same dye. This dye is an electron donor, so that is capable of giving an electron to a very strong electron acceptor. And we have an electron acceptor which is known as methyl valigen. So my dye, when it is excited, it slowly transfers its electron to the methyl valigen, and it gets oxidized, and the methyl valigen accepts the electron. And the methyl valigen has a particular property of giving an absorption spectra like this. When you do a laser flash photolysis, when you shine your light with shine your molecule with a laser flash, the molecule gets excited, and immediately the electron is transferred into methyl valigen. So in a sample, in a cuvette, a four-sided cuvette, what you do is you put the sample, you put some amount of methyl valigen also, and when you shine a laser light, the methyl valigen, which has a characteristic absorption at 385 nanometer, that can be monitored, and the growth of the methyl valigen can be observed. So we have a standard with this ruthenium plus bipyridine, and my molecule is named as RUDA2. So when you consider for the same concentration of my molecule with the standard, for the same incoming excitation light, for the same amount of methyl valigen, you can see the intensity of methyl valigen with my molecule is methyl valigen MV plus, that is the reduced state of methyl valigen, is more compared to that for the sample. That simply means that my molecule RuDA2 is a better electron donor compared to the standard value. So my sample can be utilized for giving can be utilized for preparing a solar cell, and that was my study. So electron transfer process can also be studied using laser flash photolysis. This is another molecule which also is to be reported, and this also has a very high electron transfer capability compared to standard. So these are the various studies which you can do with laser flash photolysis study. So maybe for the last 1 hour you have been patiently listening to me on UV visible fluorescence and laser flash photolysis, and I once again thank the coordinators for giving me an opportunity to present my topic. I personally, as Smitha teacher was saying, I am a public speaker. All my talks and my publications and my paintings and photographs, everything is available in my website www.aravindk.in. So if you are interested in knowing science videos related to physics, maths, whatever it is, science video, you can go through my channel. My channel name is Know Science, Live Science, and there has been so many government utilities because of this channel, and I am very happy about that also. So once again, I thank all the audience for patient listening, and I'll be happy to answer a few questions.
Thank you, Aravind, for your nice presentation. And you started from basics and explained the concept very well. I think all of you have enjoyed the session very well. Now the session is open for discussion. If you have some queries, you can type in the chat box.
Okay, MSDBP is something that is the code name given to that particular molecule. That's all. I mean, it has nothing got to do with Hiba. She asked a question, MSDBP. It's actually a code name given to that particular molecule. Nothing got to do with science.
Aravind, there is one more question from Satyendra Kumar.
Yeah.
And he asked, what is the relation between UV and IR?
Relation between UV and IR. I mean, I didn't understand what he meant. UV visible, even it deals with totally two different aspects, right? UV visible spectra deals with absorption of molecule in UV as well as visible light. IR deals with vibrational spectra of the molecule. What I actually try to say in that particular fashion, maybe that created the confusion. Whenever you are dealing with the UV visible absorption spectra, which is in the U-shaped spectra, it includes the vibrations also. That is all what I meant to say. I never meant to say that IR spectra is encompensated in UV visible spectra.
And one more question here from Aisha Sumro.
Sure.
Is it necessary to calibrate instrument with respective solvent in the sample?
Calibrate the instrument with the respective solvent. No, that is not necessary. It all depends upon what you do. Normally you don't calibrate the instrument with the solvent because you are already using a blank for the solvent. So that is not at all necessary.
Okay.
And when you are dealing with laser flash photolysis, you always have to deal with, always have to purge nitrogen or argon or any of the inert gas through that, because the presence of oxygen is actually a big poison. Oxygen, since it is present in the triplet state, you always go for a laser flash photolysis studies for only those molecules which you expect having a triplet state in the excited state. So if you have oxygen in the triplet state, what happens is the oxygen in the triplet state as well as your molecule triplet state, they combine, and the oxygen gets gone to the oxygen actually gets converted into the single state, and the molecule will be de-excited. And as a result of which, you won't be able to study any of the excited states. So whenever you are taking a sample for laser flash photolysis, you pass nitrogen gas or any of the inert gas, make it air free, and only then you go for laser flash photolysis.
Okay. If you have no doubt,
teacher, there are more questions. I think, how can I prepare solution for UV analysis? Amount needed.
Okay. The amount needed is
One
the
question.
concentration is lesser than 10 raised to minus 6 or 10 raised to minus 7, because the maximum absorbance which you can get is 2 only. That's the maximum absorbance. So more dilute the solution is, the better absorbance and the better vision of your spectrum would be. So an ideal concentration would be 10 raised to minus 6 or 10 raised to minus 7. Anything lesser than 10 raised to minus 5. So what you can do is, if you have a small 10 ml standard flask or something like that, you take the lowest possible standard flask, maybe 25 ml or 10 ml or 50 ml. From if 50 ml is something which is available to you in the college, take the 50 ml. From there, you take 1 ml, you dilute it into again another 50 ml. From there, take 1 ml, you dilute it into another 50 ml. You dilute it such that the concentration is less than 10 raised to minus 6 or 10 raised to minus 7. You will be getting a very important spectra. Never prepare a sample by giving a spec if you are doing some quantitative study. If you are just doing a qualitative study, there is no harm at all. You put a very small piece of sample, and that is more than enough. But if you are doing a quantitative study, make a stock solution from.
Sir, one more question about laser dyes.
Yeah.
Laser dyes.
So what?
The question is that, can you brief about laser dyes?
So what on laser dyes? Because laser dyes are totally different from laser flash photolysis.
Excuse me, sir. Can I ask you a question?
Please.
So myself, Dr. Haripatnam from NSS College in Amara.
Please.
As part of a project, we have prepared a dye-doped film, that is natural dye-doped polymer films.
Okay.
With varying doping concentrations.
Okay.
And what we have found that the UV visible absorption spectra, the intensity increased with increase in doping concentration. But when we have taken PL, photoluminescence, the intensity has diminished after some particular concentration. So can you suggest me what can be the reason for that?
Can you tell me once again?
With increase in doping concentration, the UV visible absorption spectra intensity increases,
Okay.
but the photoluminescence spectra intensity decreases from a particular value.
Okay. So it is not the artifact of the instrument, right?
No.
No.
We have repeated that.
Oh, okay. No. Like I didn't make fun of you because all such things are happening. Can you just send me the spectra? I will look into it. This is my WhatsApp number. So unless and until I see the spectra, I won't be able to give you any conclusion, right? Normally it shouldn't happen. That's why you asked me the question, right? So I'll just look at the spectra and I'll tell you.
Okay, sir. I'll mail to you. Thank you.
Aravind,
yeah.
There is one more question.
Please.
What are the flash photolysis application? What are the flash photolysis application?
One thing is, you know how the molecule. First thing is, you will be able to know whether the molecule is in the singlet state or the triplet state, because molecules in the singlet state has so many applications. Molecule in the triplet state has some other applications. Okay, that is the first thing. The second thing is, for processes like solar cells, or processes like if you are trying to mimic photosynthesis, if you are doing some photodynamic therapy studies, then electron transfer is very important. So the rate of electron transfer, the kinetics of electron transfer, the excitation time, all such data will be obtained from laser flash photolysis studies. So when you get all these data, you'll be able to design such systems which actually efficiently acts as a electron transfer system. So these are the two major applications of laser flash photolysis. It is seldom used. It is not used by everyone.
I think there are no more questions here.
Okay, you can be free. You can contact me anytime. My WhatsApp number is given. You go to my website. My email ID is also there, so you can contact me anytime. No issues. I'll be very happy to. Maybe in WhatsApp when you give, maybe within 1 or 2 days I will definitely reply. I travel every day. So.
Okay.
Rate of electron transfer during photosynthesis is so yeah, definitely we can measure rate of electron transfer during photosynthesis. That is something which I showed you of methyl violin. I just showed you the growth of methyl violin, right? From that intensity, we can directly understand the rate of electron transfer. Name of my YouTube channel is No Science, Live Science. have a Facebook page on that. So photolysis is basically you are splitting your molecule splitting your molecule in the presence of light. That is basically known as photolysis. So laser flash photolysis is known as photolysis just because your molecule always has a possibility of getting disrupted. You won't be getting your molecule back. So you are lysing your molecule. You are actually breaking down your molecule. That is the main why it got its name.
Okay.
Okay.
Okay. Now, if you have no queries, we are concluding the session today. And on behalf of me and Department of Chemistry, NSS College, Manjeri, I express my deep gratitude to Mr. Aravind K for your wonderful session delivered here.
Thank you.
And I invite our HOD, Dr. Bijidas K, for concluding the section here. Thank you. Bitu sir.
Sorry, are you audible to me now?
Yes, sir. Yes, sir.
Okay, okay. Thank you,
Yes.
thank you. Thank you. I'm very much proud of to my team, Dr. Yamuna, Smita, Bashpa, and Vineet, and our former HOD, Sindhu teacher. Actually, this seminar series was a very success part, and we have very good presentations. We have 4 very good topics. 4 eminent personalities have conducted the program. Unfortunately, Dr. Hari from Switzerland, he was unable to deliver his talk, and we are thinking of planning one more series mainly on nanotechnology. And I thank all the participants here on behalf of the Department of Chemistry. I thank all the participants here, and especially my sincere thanks to Dr. Professor Aravind for his nice presentation. And I am formally I am thanking my team also. Thank you very much. I am handing over to the coordinator, Dr. Yamuna. Please.
Thank you, Vijay sir. Good afternoon to all participants and our today's resource person, Mr. Aravind. And actually, I'm very thankful to all of you, all of those participants here, because this is a series. We planned it for 5 lecture series, but unfortunately, we had to restrict it up to 4 lectures due to some unfortunate situations from Dr. Hari and us. But during all these sessions, all these participants sticked on to us, and they were very inspiring. Actually, they were calling in between, like giving some positive feedback and personal messages and the calls we received and emails also. And this actually inspired us, and this motivates us to go for another sessions. And also the resource persons were also very satisfied about the participants' interaction, the questions asked, and so. And also the most unfortunate thing we had is the selection of resource persons. The first session was handled by Dr. Pritam Bharadwaj, and then Sajni Vadukumpulli take over, and then we had Dr. Aravind Rajan Medikalam, and we are now ending with Mr. Aravind K. And all this proved to be very eminent and excellent resource persons actually. And these people, the participants gave very good feedback to us, and we are thankful to the participants who stick on to us, and again, as I said, motivated us for another series. And we will be, as Vijay said, we will be going on with the another series like this, and you will be our high priority invitees. And we expect this cooperation in future also. And actually, this we formed like a group, and we can collaborate for academic and research reasons also. Some relations developed like that, but between the researchers, resource persons and participants, etc. So we are very successful. I would say we are really successful on organizing the webinar series in this tough time of pandemic that we are going through. And yes, I'm very thankful to the participant and also to all those resource persons. And with an apology, I regret to say that we had to cancel the session from Dr. Hari. And he offered to give another session when he is back in full health, and let's hope to meet again, including Dr. Hari there. And because we don't want to disappoint you, or we expected to have a nice NMR session, and that's why you joined here. And so I hope we will not let you missing that session. And in soon future, we will do that, I hope. And I thank the team, as Vijay said, the team chemistry, as I always wrote to you. Officially, yes, but and also other colleagues from the college, the NSS College Manjeri, especially our principal, Dr. R. Sarjan, who always encouraged us. And thank you all. And I would like to give an information on certification. You will receive a feedback form, because this was a question frequently asked about the feedback form and certification. The plan was, as I explained in the beginning, the plan was to give a single certificate at the end of the series. So you will receive a certificate. But before that, this week, you will receive a feedback form. And after submission of the feedback form, you will automatically receive a certificate. So please wait, please expect the feedback form for the whole during the week, because due to the number of email restricted by Gmail, we cannot contact you all on a single day. So please wait the whole week, and then you will receive a feedback form followed by certification. And yes, thank you. And yes, I would like to have my colleague Bashpa to speak up here. I would like to have you here, Bashpa. Bashpa?
Thank you, Yamina. Good afternoon, all. And I'm very happy that we are having a successful webinar series with 4 nice talks and nice presentations. And I would like to thank all the participants for your cooperation and active participation, and expecting this in our coming series also. Thank you all.
Okay, so let's stop for the time being, and we will see each other with a new series. And yeah, thank you and bye-bye for the time being.
Thank you all. Thank you all.